When we look at colloidal stability, we can see that there are two conflicting interactions. We know that there's a Hamaker attraction between any two particles if they're identical, whether or not they're separated by a solvent. And that's going to tend to destabilize the colloid because it's going to bring the particles together. On the other hand, we know that there's repulsion between the particles due to, it's an electrostatic repulsion due to surface potential. So as long as the surface potential is not equal to zero, the particles are going to repel each other. So the stability of a colloidal system is going to depend on the balance between these two interactions. Electrostatic repulsion, which pushes particles apart and thus stabilizes the colloid, or Hamaker attraction, which pulls them together and tends to cause the dispersion to destabilize and coagulate. So this is summarized by just putting together the expressions for both repulsion and attraction. And that's what DLVO theory is. So DLVO theory is just the sum of attraction and repulsion. So we'll do an expression for spheres. We're going to write an expression for spheres of the same radius. So we have the radius of the spheres, and then the appropriate Hamaker constant. So if we had spheres that were identical, of course they would be, and they're separated by a solvent, this would be H121. So in this expression we have the radius of the particles, the appropriate Hamaker constant. H is the distance, the face-to-face distance, not the center-to-center distance between the particles. Here we have the concentration of salt in ions per meter cubed, Boltzmann's constant, the temperature in kelvins, gamma, cap gamma naught, remember, is that hyperbolic tangent. I'll write that again in the bottom just to remind you. And kappa is the inverse Debye length. Okay, let's also write the expression for plate-like particles. And as a reminder, cap gamma naught is just a hyperbolic tangent, and it's a ratio of electrostatic energy over random thermal energy. Note that since we only have one number in here for Z, this is a simplified expression for symmetric electrolytes. So +1, -1 electrolytes, or +2, -2 electrolytes, etc. Let's graph the expression for these curves. So if we graph potential energy as a function of distance between the particles, we get a curve that looks something like this. Now this curve is a little bit misleading because it looks like we could just keep lowering our potential energy until the distance between the particles is zero. But of course, if we get them less than one atomic distance between the electron clouds from one particle, will bang against electron clouds for the other. So we have a Born repulsion curve, which is just the particles smashing into each other. And that curve would look something like this. And so if we add those two curves together, we get the overall energy, the one given by the equations on the previous page, plus Born repulsion, and we get an overall energy curve that looks like this. So only the right-hand part of this curve over here is what's predicted by the equations on the previous page. Okay, so looking at this curve, we can see there's a couple of features. We have what's called the secondary minimum and the primary minimum. And these represents basically there's a potential well that you can fall into that's very shallow, that's easy to get out of. And there's a deep potential well that you can fall into that essentially is irreversible. If you're stuck here, your colloid is dead. All the particles are stuck together. And in the literature, you will sometimes see coagulation and flocculation used completely interchangeably. Some authors don't do that, and they like to make a distinction. They call this potential well the one for flocculation, and the deeper potential well, coagulation. Unfortunately, that's not universal, so some people use the two terms interchangeably, and some actually make the distinction here. So you're going to have to let's leave that off. The important point to know is that if your colloid falls into this potential well, this is going to be irreversible. Whereas over here, if you fall into this secondary well, just by agitating or sonicating, maybe even just shaking up your colloid, you can redisperse the particles. Over here, that's not true. It's a dead colloid. Depending upon the values of the Hammaker constant and the surface potential, there may be, between the two potential wells, the energy of the curve may go above the zero of potential energy. And we'll just call this Vmax. And when Vmax is large, if Vmax is much greater than kT, that means that your particles will come, they'll be weakly attracted to one another, and then as they get closer, the energy goes up and they'll bounce away. And basically you won't be able to get into this well. And that means that you'll have a stable colloid, because you have, this represents the electrostatic barrier to going into the primary minimum and coagulating the colloid. We can affect the size of this barrier by changing the ionic strength. We know if we increase the ionic strength, it's going to shorten the Debye length, and that is going to weaken electrostatic repulsion, and that's going to force this to go down. And eventually, this will get to the point where we have zero energy barrier to coagulation. That's called rapid coagulation. The salt concentration it occurs is called the critical coagulation concentration, and it's the subject of the next few screencasts.